Good afternoon. My name is Jay McKinley, and today I want to talk to you about my DSA 5793 multivariate statistics, PCA package, and PCA data analysis. The agenda here is I'm going to first cover a few things about my PCA package, which is the package I designed, and then I'm going to talk about the data analysis I did on digit identification using that package. So my motivation behind the package was to understand better how principal component analysis works, and then to create a package that had not only calculated the principal components, but also produced some pretty neat looking graphs, and it built in a predict function that would do a prediction based on the data. So the first thing I did is I made sure to add a small subsection of the digit data, and so that if somebody else wants to play around with it, they don't have to go and try to find this data. It's right there within the package. Next thing I did was create the PCA function, and what's neat about this function is it takes just in a data frame matrix and a label and actually outputs a PCA class that has a few different things in it. That has the rotation, which is the eigenvectors, the eigenvalues, the standard deviation, which is the square root of the eigenvalues. It actually returns the rotated data, and then a few other things, including this optimal split, which is an outside function I brought in from another person, and it actually calculates kind of where the bend in the curve is on the proportion of explained variance curve, and that way you can have an idea of where to do a split at if you don't want to just look at the graph and guess yourself. It also includes some plots. The first one is the base plot. As you can see here, it overrides the plot function. It takes in the DCA, the digit PC or the PCA data type, and if you tell it what the label is, it gets this nice colors that you see here, and you can start interpreting the data from there. If you add text equals true, it'll actually put the label over the top of them, and you'll see that in a later graph I show. Here's the scree plot, and this has two different calls: the scree plot, which overrides the base scree plot, and the GG scree plot. Either way, if you send it the digit.pca data class and the number of components you want to look at, it plots the proportion of explained variance or the cumulative proportion of explained variance, or if you don't tell it, it does both, so it shows you both here. And then the predict function takes in the PCA class, a new matrix of data, which is it has to be in the same format, where the label is the whatever column, and usually the first, and then the rest is all the digit data information, and then it does a prediction on that. And as you can see here, it does a pretty good job predicting. It does mess up a couple times. We're not using a whole lot of data here, but it's neat. It works. It's a little bit slow. I think, as I'll talk about later, it needs to be optimized a bit, but I think it does, considering how good a job it does predicting just using the matrix math or linear algebra. It's pretty neat. So the next part is the data analysis, and we're going to use PCA for digit identification. So the introduction here is that I think it's just an important topic to understand how to use PCA to reduce the number of features you have in your data. It's also interesting to understand the theory behind that what you're doing is actually taking this this data that's has a lot of correlation, and then rotating it so it's multivariate normal, and so that the covariance between any two variables is 0. And I think that's really neat. We do lose some predictability with that. Not predictability, I'm sorry. We lose some explainability with that, but that's fine. For some projects, that's not a big deal, like this one, where all the features are the same anyways. Them kind of coming together into a single feature isn't such a bad thing. And so that's what we're kind of showing here. A little bit about the data. We have 30,000 in the training set to work with, and our test set is only 7. In the actual analysis, I actually subset the data, the training set, down to 15,000, and then I make a bigger test set along with this test set, just to learn more about it and better testing of it. Here's the distribution. As you can see, almost all of them have 3,000 digits. And so here's a neat thing. So we're going to scale the data. So the data goes between each point on the bitmap is between 1 and 255, and the way we display the images with the computer, it likes them between 0 and 1. And so that really doesn't change the data, what we have to do with calculating the PCAs and stuff all that much. So we just divide everything by 255, so we get this number between 0 and 1 instead of 1 and 255. And as you can see here, if we do that, we get this image. And then when we print it out, it looks like this. The other way it comes out, and I think I show it in the analysis, you can barely see the image in there just because everything's so high. And so that's just what we got to do. And so that's a test image. Here we're subsetting down to only 15,000 of the data, and then we run the DCA, the JPCA function to get our PCA class. And then we're going to throw it up there in a plot real quick, and you can see, just looking at the first two dimensions, the PC1 and PC2, you can see there's definitely some areas where predictability would be very high. So if we get, when we calculate the squared general distance, these are all going to be in the same general area. Same with zeros over here. So I think that's pretty neat. And here's just if we want to subset down a little bit, and here we can see the numbers right next to the points. Just a neat feature of the package I wanted to demonstrate. So here's the correlation of the data, and as you can see, it is very highly correlated. This may be something I should have talked about before the doing the actual PCA, but this correlation is what gives us the ability to rotate it and get these new principal components. And so by looking here, we can see there's a fair amount of correlation, and so this is going to work fairly well. And the mathematical theory here, I'm not going to read this to you. However, it's important to know that with multivariate statistics, a lot of our assumptions depend on the fact that we are in a multivariate normal space. And so that's using principal components, we're able to calculate the eigenvectors and eigenvalues and then rotate our data to a position where it's multivariate normal, which basically just means that the covariance is 0 and all we're worried about is our variance. And so here's the definition of principal component. As you see, the principal component is equal to the eigenvector multiplied by the data. And then when we do that, then the really great thing about that is that now our variance becomes lambda and our covariance is 0. And what's interesting about that is that the total population variance, so the total explained variance of xi is the same as the total explained variance of our new data matrix yi. And we can show this by calculating the trace of both. And as you can see here, when done in R, they are the same. And then we can calculate the proportion of explained variance. So the amount each component brings explains of the variance. And as you can see, it doesn't take long before we're getting down to only less than a 1% explained variance is added to with that feature. So at some point we just don't need more features. They're just not explaining enough to make them worthwhile. And here's our screen plot. As you can see, usually you want to pick around the bend. I like to go until I have 90% of the explained variance. That would put us in the hundreds, but still a lot less than 784 features. So we really cut down, and we still get a really good predictability. And then we got the cumulative proportion of explained variance, which we're just summing all the lambda i's up to k or up to j over all the sum of all the lambda i's. So we get, as we can see here, up to principal component 41, we explain 79% of the variance. And so if we go up to 121, 93% of the variance is explained. So we're still way below the 784 that we had originally. So we're cutting way down in features, which makes this a much more tenable problem. And there's the scree plot of just the cumulative proportion of explained variance. So here's the mean digit. This is when we do the column means of all the data, and then we turn that into a picture. As you see, it's pretty blurry, so it's all the the mean of all the images. And then if we want to reconstruct the image, we just add in principal components. And so we add in 25 principal components, and you can already start making out that this is a 7. And as we get to 500 principal components, I mean it's quite easily recognized as a 7. And so a computer doesn't need to see it. It doesn't see it. What it does is it recognizes this pattern or in our case, mathematically, it recognized that this squared general distance is in the same neighborhood as all the 7's squared general distances, and then it makes that prediction. And so that's what this prediction function does. It calculates all the squared general distances for all the data in trained PCA, and then compares that to the squared general distance that it calculates for each test case, and then predicts that as the label. And as you can see here, it does a really good job. It gets them all right, except for this last one where the actual, it was a trick question. This actual was an 11, which we've never seen before, and then it predicts it as a 0, which to me kind of makes sense because, it's got the two far side lines, and it just that's the, if the ones were curved in on itself, that's almost what it would look like, would be a 0. So I hope this makes sense. This is a quick and fast, I still went over time, explanation of how PCA can be used to do digit prediction, which is a really simple case, but could be generalized to more complex cases. And what it shows is that you can take this large data frame with all these columns that's just untenubly, the computer just can't handle it, and then reduce it down to a size that even a small computer, a small laptop like mine can handle. So pretty awesome. Thank you very much. Have a good day.